Hey everybody, in this video we're going to be talking about area by double integration. So let's remember some things real quick from previous sections and then we'll move on to the new part, which is the area. So remember that the double integral by definition of our function f of x and y over some bounded region R, which is here, is equal to this limit. So this is the limit of the Riemann sums, and just notice what we have here real quick. This would be the area of like all of the subintervals, like all the little rectangles that we cut our region into, and then this would be the height. So this is technically volume because you have height times width times length, if you say that for the area here, and then you add all these up, okay? And then if you take the limit as the norm, this part here, the norm of the partition goes to 0, that's basically saying that the largest width of all the subintervals, if that's getting super small, if that's going to 0, and you take this limit, then you pretty much get like infinite little rectangular slices, or like little volume pieces, and then that equals a double integral. Okay, so we talked about that previously, but what I want to talk about now is how we use double integrals for area. So if we let our function equal 1, so if f of x, y is 1, okay, then notice what we're going to end up with in our limit definition here. So then the limit as the norm of the partition goes to 0 of our summation is just going to become the sum of the areas delta a sub k. And so notice, because this whole part right here is just 1. And so what that gives us is a definition for area using double integrals. So we can say that the area, actually let me do this in a new color so it stands out a little bit. Okay, so we have the area of a closed bounded plane region. So the region is closed, it's bounded, and it's a plane. Okay, region is just going to be, so I'll just say area equals the double integral over our region R dA. And that's because, and I'll put it in a new color, there's an invisible 1 here. So if we take the integrand of 1, so a lot of time you're not going to see it. So if there's nothing there, it's really invisible 1. So if the integrand is 1, with our double integral, that is area. So this is a formula that we can use. Alright, so let's go ahead and do an example. Okay, so in this example, we're going to find the area of the region enclosed by y equals x squared and y equals x plus 2. So one of the best things to do first off is to draw what you're working with so you can visualize this region. And so what we're going to do is we're going to go ahead and graph this parabola first, y equals x squared, standard parabola at 0, 0. We have a point 1, 1, and then 2, 4, and then we'll mirror those points over. And let's just draw this parabola real quick. Oh, okay, you get the idea. It goes right about there. Alright, so that is y equals x squared. And then we also have a line, y equals x plus 2. So that has a y-intercept of 0, 2. Slope is 1, so we're going to rise 1 and run 1. Do that again. And we'll drop 1 and run to the left and get that line there. Alright, there, that's pretty good. Okay, so that is y equals x plus 2. And now, the problem says find the area of the region enclosed by these two. And so that is this region here. Okay, this shape. So we want to know what is the area of this region that I'm highlighting. And we are going to use double integrals to figure that out. Alright, so you have to make a decision here. You have to say, are you going to integrate with respect to x or y first? And so let's just put our double integral here. So in general, it would be the double integral over our region R. Our integrand is 1, but you can put that or you can leave it off. I'm just going to put it for now, but it's technically there if it's invisible. And we need to decide, are we going to do dy dx or dx dy? Okay, and then based on our drawing, that's going to help us make this decision. And so these are our two choices. And let's take a look at our region over here and figure this out. Now, if I start taking cross sections of my region horizontally, look what happens. I'm going to enter the region at the line and exit at the parabola. But if I just enter a little bit lower, if I'm down here, I'm going to enter the region at the parabola and then exit at the parabola. So I would actually have to split this region into two separate double integrals if I wanted to use horizontal cross sections. So I'm not going to use horizontal cross sections. I'm going to go ahead and use vertical cross sections. And if I just enter from the bottom, wherever I decide to enter the region in from the bottom, it's going to be the parabola, and wherever I exit at the top is going to be the line. And so that's only going to be one double integral that I have to work with. And so we're going to use this version, integrating with respect to y first. Okay, so we're going to have our double integral. Remember, integrand is 1. We're choosing dy dx. And so our region R, we're integrating with respect to y first and x second. So a lot of times it's easier to start with the outside integral. Let's do that really quick. Notice that with x, in your whole region, this is blue highlighted region, x goes from -1 and stops at 2. Okay, so this whole region is in between the values x equals -1 and +2. Okay, so that's my limits of integration on my outside integral with respect to x. Now, with respect to y, notice what's happening when you enter your region here. You're entering at the parabola y equals x squared. So it's already solved for in terms of y, so we didn't have to do any extra solving over here. And then we exit the region at the line, which is again already solved for in terms of y equals x plus 2. Alright, now you don't technically have to put the y equals here and x equals, but I'd like to do that just so that I keep track of what's going on. So now that we have this setup, that's honestly the most work that we have to do. The hardest part is coming up with this setup. Once we have this, it's not too bad integrating. So we're going to go ahead and do the inside integral. We are going to integrate this first one with respect to y. Alright, so I'm going to just leave our second one on the outside for now. And then we're integrating with respect to y. So the integral of 1 with respect to y is just y. And we're evaluating that from y equals x squared to y equals x plus 2. And then we still have to, let me put parentheses here, we still have to next integrate with respect to x. So let me make sure I put that on there and don't lose it. Alright, so integral on the outside is still there. And on the inside, y, we plug in the upper limit. So it's x plus 2, and we subtract plugging in the lower limit. That's x squared. Oops, let me make that look better. Okay, and then we still have our dx over here. And then this is a good way to make sure we're on track. Our variable that remains is x, and then we're integrating with respect to x. And then we only have numbers in our limits, so this is going to work out. Okay, so let's keep going. So from here, if I'm integrating this, I just have integral of x is x squared over 2. Integral of 2 is 2x. And integral of -x squared is -x cubed over 3, all being evaluated from -1 to 2. And then we just plug in these values. Let me just do that for you really quick. So 2 squared over 2 plus 2 times 2 minus 2 cubed over 3, and all of that, and we subtract plugging in -1. So -1 squared over 2 plus 2 times -1, that's a -1, minus -1 cubed over 3, and if you simplify that, you will end up getting 9/2, or 4.5, and so that is the area of our highlighted region. Okay, now just for fun, I'll show you what the integral, double integral would look like if you were doing this with respect to x first. We won't work it out, or you would get the same answer, but just so you know, if you did end up doing horizontal cross sections, you would have to do two separate integrals. You would split this into two regions. I'll just kind of highlight the difference here. You would have like this lower region, and then the upper region, let's just go green. Well, that's gonna not work. Let's go pink. This upper region here. Okay, and then the split would be right here. Okay, so you would have to do something and call this one like R1, and you would call this bottom one R2, and then that would just, so you'd have it, you can check if you want to, that would look like you would have x goes from negative square root of y to positive square root y, and then y goes from 0 to 1. So y goes from 0 to 1 here and here. X goes from the negative part of the parabola here to the positive part. And then your integrand is still 1. Dx, dy. but then you would have to add the double integral of the second region, and that would be x goes from y minus 2 to square root y, and y goes from 1 to 4 dx dy. And that's up here. You enter in at the line. We have to solve in terms of y. That's why it's x equals y minus 2. And you would exit at the parabola, and that's why it's x equals square root y. And then y goes all the way from 1 up till 4. Okay, you get the same answer though. So just, if you want to, for fun, you could check. All right, let's try another example. Okay, so this example says find the area between -2 and 2 for x, and y is between -1 minus square root 4 minus x squared and 1 plus square root 4 minus x squared. Okay, now if we draw this, and we're not going to draw this one, you would see that this area is very symmetric. It has symmetry about the x and y axes, so you could actually do some simplifying with your double integral here, and pretty much you can cut your region into a quarter of the region, and then using symmetry you could just like integrate that quarter region and then times your answer by 4. But either way, we're gonna actually just do it straightforward. We're gonna say that x goes from -2 to 2. Sorry, that's a -2. Hopefully you could tell. And y goes from what we have given there. And now the way that you know, like right here on this one, your only option here is to integrate with respect to y first, because if you notice, y is given in terms of x, and x is just constants. So you have to integrate with respect to whatever has variables in it, pretty much. Like, that's an easy way to remember. So notice that y has the variable x in the bounds, so we have to integrate that one first, okay? So dy is first, and then dx. Okay, so let's go ahead and just start integrating. So the setup was easy on this one because of how it was given to us. We didn't have to come up with the bounds. So we have just integral of invisible 1. Remember what I'm doing here? I'm just focusing on the inside and integrating this with respect to y, and there is an invisible 1 right here. So the integral of 1 with respect to y is just y. So we are evaluating y, and I'll just sort of skip some steps to save some writing, but we're evaluating y at the upper and lower limits. So the integral of 1 is y, and then we plug in the upper limit and subtract, plugging in the lower limit. So that's all I'm doing here. I'm just sort of just skipping the one step where I write y. Okay, so the upper limit minus the lower limit, and then we'll do some simplifying, and then we'll integrate this. Alright, so all that's left is dx. Notice your only variables remaining are also x, so that's a good sign. Alright, so if we simplify this a little bit, let's see what we can come up with. We have, just combining some terms, 2 plus 2 square root 4 minus x squared dx. Alright, so now let's separate. We can integrate 2 on its own, and then our second integral will have that not so fun radical that we have to work with. Okay, so our second integral, I'm going to factor out that 2 to the front, and then we have the square root 4 minus x squared that we have to work with. Alright, so this one here, we know what that is. That's just going to be 2x evaluated from -2 to 2, and so that's just going to give us 8. Alright, so that's 8, so that one's done. We're going to just remember that that's part of our answer, and then we're going to focus on the second integral here. Now, in order to do the second integral, because we have this fun radical, we're going to have to do trig substitution. So let's see what you remember about this. So this is hopefully something that looks familiar from your past calculus experience. So doing some trig sub, we are going to let x equal 2 sine, whoops, that says sine theta, and then the derivative of that is going to be 2 cosine theta, and then d theta. So derivative of x with respect to theta, then timesing by d theta. So technically, like if you think of this being down here, then you multiply by it to get it over there to the right side. Alright, so I make this choice for x. Okay, well, you said we're going to let x equal 2 sine theta, and I won't get into this because hopefully this is something familiar to you, but if not, please just review trig substitution. There are specific things that you want to substitute in to your integrand and in this case 2 sine theta is going to help us with this, simplifying this, this radical right here. Okay, so from here, what do we have? We have to change our limits because we're substituting. So let's do that really quick. We know that x is 2 is our upper limits. So let me just write what I'm talking about. We're working with our limits of integration right now, so we have to change them since we're substituting. So our upper limit was 2. So based on our substitution, we need a new upper limit. So we know that x is 2, but we said x is 2 sine theta, okay, based on our substitution. And so if you just take a moment and you solve for theta, because that is now your variable you're integrating with respect to, you would end up getting that theta is pi over 2. And then your lower limit, x was negative 2, same idea. We said x is actually 2 sine theta, and so if you solve this for theta, you would get that theta is negative pi over 2. So these are our new limits of integration over here, okay, since we're substituting. All right, so now from here, let's go ahead and plug these things into our radical, into our integral, and then the radicand. Okay, so remember that 8's still in the front. So we have so far 8 plus 2 times our integral. Our new lower limit for theta is negative pi over 2. Upper limit is pi over 2. And we have square root 4 minus what we're substituting for x, which is 2 sine theta quantity squared. Okay, and then we had a dx in the back here, remember, so we have to substitute that as well, and that's 2 cosine theta d theta. All right, so let me just highlight a couple things so that you are on track with what's going on. Okay, so x, we chose x to be 2 sine theta, so right here we replace that. Okay, and then because we're substituting, we had to change, account for our dx as well, and so dx is just the derivative of 2 sine theta, and so where we had a dx, we substituted that. Okay, and then last, because we're doing substitution, we need to change our limits of integration, and so we had our upper limit. We figured out when our upper limit was 2, that corresponded to pi over 2 in terms of theta, and when our lower limit was negative 2, that corresponded to negative pi over 2 for theta. Okay, so hopefully that kind of sums up what just happened there. And now why in the world did we do all this? It's because this actually helps us integrate this radical that was actually very hard to integrate before we did the substitution. Believe it or not, even though it looks uglier, it's actually now much more able to be integrated. Okay, so let's work this out. All right, so again, that 8 is still in the front, plus the 2, and then what we end up getting here is the following. So I'm going to bring the 2 out to the front. That's this 2 right here, and I'm going to factor out a 4. Okay, I'm going to show you where that came from really quick. Let me just kind of put this cosine theta back on here. All right, so I factored out a square root 4 because if you notice what you're going to get, you're going to get a 2 squared, which is 4. So I factored out that square root 4 right here. And then what's left, if I factor out the square root 4, is 1 minus sine squared. Okay, so I just sort of skipped that step of showing it, but I factored out a square root 4 from here and here. That's where the 1 minus sine squared came from. And now why did we do all this? What was the whole point of all this? It's because, look what happens here. This is one of your trig identities. 1 minus sine squared is cosine squared theta. And then if you take the square root, because notice you're still under the radical, then you end up with 8 plus 4 integral. Actually, let's go ahead and change this really quick just to save some time. Square root 4 is 2, so this is just going to be another 8, okay, because it's the 4 in the front times this 2. And then we have right here, this is where I'm focusing, square root of cosine squared is just cosine. So I have cosine, that whole thing just became cosine, and then there was already a cosine in the back, so this is again cosine theta in the back, and so we have 8 plus 8 integral cosine squared theta d theta. And okay, so from here we have to use something else we learned previously. So the trig substitution you learned in in probably your previous calculus class, but the next thing I'm going to do here is something you learned from trig, so I'll put it off to the side, but recall, so this is one of your trig identities, that cosine squared theta equals 1 plus cosine 2 theta over 2. So this is one of the identities that you learned from trig, and you want to remember this one anytime you're trying to integrate cosine squared, which we are. Okay, so now we have 8 plus 8 over 2, because I'm factoring out the 2 from the denominator over here, times our integral 1 plus cosine 2 theta d theta, and then let's just keep going. 8 plus 4, let's go ahead and separate these. This is going to be our integral of 1 with our limits negative pi over 2 to pi over 2 d theta, and then plus 4 times integral negative pi over 2 to pi over 2 cosine 2 theta d theta. Okay, now as we continue, we have 8 plus, this is going to be 4 times, and then we're just integrating 1 with respect to theta, which is just theta, and so integral of 1 is theta, plugging in our upper and lower limits for theta. So that's just going to be pi over 2 minus negative pi over 2, and just make sure that we distribute that 4, so let me put brackets, plus 4 times, alright, technically we need u substitution, so you could do this without it, but let me just show you, without writing it, but let me show you. U is 2 theta, and so du would be 2 d theta, and then substituting that, let me just divide out that 2 from the d theta, and we have integral of cosine u du. Right, now my limits, I would technically have to substitute for those as well, or I can leave them and just resubstitute at the end here, which is what I'm going to end up doing. So we have integral of cosine u, which is just going to be, if I have the 2 in the front here, let's just focus on this integral, 2 times sine, it would be u, but I'm going to just go ahead and resubstitute and say 2 theta. And so now I can say that my limits stayed as negative pi over 2 and pi over 2, and plug those in. So we have 8 plus, this becomes 4 times pi, because it's just 2 pi over 2, plus 2 times sine of 2 theta, but we're evaluating that at pi over 2 and negative pi over 2. So if we plug that in for theta, we just get sine of pi minus sine of negative pi. Okay, so we have 8 plus 4 pi plus 0, because sine of pi and sine of negative pi is both 0, and so 2 times 0. So final answer, 8 plus 4 pi is the area of our region. So we did it. Yay! Alright, the last thing I want to talk to you about is average value. This is going to be the average value of a function over your region R. And so the formula for this is the following. It's still your double integral, okay, but I'm going to put something in the front here. So it's a double integral over your region R of your function f dA. But the way you get the average value is you actually divide by the area. So you say 1 over the area of R. So if you're asked to calculate the average value, you're going to do your double integral of your function, but you have to remember to divide by the area. Okay, so you might want to calculate the area first, and then just remember at the end the double integral of your function to take that answer of the area and divide by it. Okay, so let's just say that f is a function that represents temperature. So then your average value would be your average temperature. And you could say like maybe over the course of like a month or something. If f is a function that represents distance, then average value, this double integral divided by the area, would be the average distance. Okay, so let's try an example. Okay, so we're going to find the average value of a function f of xy, which is going to be in this case x cosine xy over this region R. Notice this region is just going to be x is from 0 to pi and y is from 0 to 1. So if the region wasn't so nice, like this one's a nice rectangle, we would do what we just did. We would use a double integral to find the area But for us, we could go ahead and just use a little bit of geometry here for the area of R. Again, one more time, if the region wasn't so nice, you would just use your double integral to find the area. This time we're just going to say, okay, x goes from 0 to pi, so the distance there, I mean, you don't even have to write this out. We know that that distance is pi. And then we know that y goes from 0 to 1, so that distance is just 1. And so the area, think of it like length times width, just pi times 1, which is just pi. Okay, so we are going to end up, I'm going to just put a star by this, because we need this later. We're going to divide by it. Okay, or we can just keep it in our work the whole time, if you remember to put it in the front. And so the average value of this function is equal to 1 over the area, so 1 over pi times our double integral. Okay, and so in this case, either way, as far as integrating goes, we can go with respect to x or y first. In this particular one, I'm going to go ahead and say that it's easier to integrate with respect to y first. So I'm going to say dy dx. So then y goes from 0 to 1, x goes from 0 to pi, and then we just start integrating. So the only difference here is that we have to remember this part in the front. Dividing by the area gives us what's called the average value. Okay, so in this one, we're going to do a little bit of u substitution really quick. Let u equal xy. So du, in terms of y, is going to be x dy. So if we integrate differentiate u with respect to y, we're going to get x dy. And so if we substitute, let's just do this step really quick on the side here. This is going to be 1 over x. Du is going to replace dy. Okay, so keep going. We have 1 over pi. Integral x goes from 0 to pi. And then this integral here, technically I should change my limits since I'm substituting, but I'm going to just wait on that. And I have x here, and with the dy when I substitute, that's going to be 1 over x, so that x is going to divide out. So I have, let's just cosine u du and then dx. Okay, so hopefully you tracked all that. That is the u, and then 1 over x dy. 1 over x, du is replacing dy, so that this x right here divided out. Alright, so now let's just integrate this inside integral with respect to u. So we have 1 over pi, integral 0 to pi, integral of cosine is sine, and technically it would be sine u, but I'm going to go ahead and resubstitute and say that's xy. And then that's going to have me put my other limits back on. My limits in terms of y were y equaled 0 to 1. Okay, let me kind of just group this here, make it a little bit more clear, and then dx. Okay, so keep going. 1 over pi, integral 0 to pi, sine, if I plug in 1 and 0, that's going to be sine of x, and then sine of 0, which is 0, so I don't even need to write that one, dx. Last part here, integrate sine of x now, so 1 over pi, integral of sine is negative cosine, so that's going to be negative cosine of x, evaluated from 0 to pi, so let me just plug those in. So upper limit minus plugging in the lower limit, and make sure I keep track of my minus sign here because there was already a negative on the cosine. So we end up getting 1 over the pi, that was 1 over our area that's been in the front the whole time. Cosine of pi is 1, so it's negative, that's negative 1, so negative and negative is positive 1. And then that becomes also a positive 1, cosine of 0, but with the 2 minus signs. Final answer, 2 over pi is our average value of this function over that region. Okay, so there's some examples about using double integrals for area and also to find average value. That's it for this one. Thanks for watching.